Thank you, Bob. And thank you all for coming this morning. And as Bob said, I'm going to report progress on the task of identifying a promising file format identification technology for use in NARA archival processes. This is just one area of a larger research project that has been just approved and will extend over the next 4 or 5 years. The motivation for this work is that archivists need the capability to preserve digital records. And to do so, they need to be able to identify the file formats of those digital records. And the reason they need to be able to do this is, among other things, that in appraising records that are important for preservation by the archives, there's an appraisal process that reviews records created by federal agencies. And if they are judged to be of lasting importance to the public or to the history of the nation, one identifies what file formats they're in so that one can be prepared when they are transferred to the National Archives to preserve them. And when the records come in, there needs to be a test to see that there's compliance with the agreement as to what the formats of the records will be that are being transferred. And of course, once the records are at the National Archives, there's a need to plan to have viewers or players for these file formats that are preserved, and to determine which viewer or player is needed, one needs to be able to identify the format of the file. Of course, there are thousands of different formats, and each year hundreds of additional formats that are being created and used in various applications in the federal government. And due to technological obsolescence, some of these file formats that have been used in the past are no longer used today, and there may not be software that allows one to view or play them. And so the archives has to endeavor to plan how to convert the many formats into some standard formats or current formats for which there are viewers or players. And to do so, one needs to identify what those file formats are. The archives there are hundreds of different methods of archiving files. RAR, zip are two of the most common, but in the past and even currently there are still scores of other file formats. One needs to be able to identify the fact that a file is an archive file. And there are things called self-extracting archives that are actually executable files. So you need to distinguish those self-extracting archives from other executable files because there may be user-created files in them. So there's a need for that identification of those kinds of files. One also needs to identify whether or not passwords or encryption have been used with a file. And those are an aspect of identifying the file format. So you may know the format, but you also need to know whether or not it's encrypted. And so that you can, the National Archives could prepare to decrypt files that had been encrypted. And it's also not uncommon that digital files over time may become damaged. And when they're damaged, one needs to be able to identify the file format and to then consider whether it's possible to recover at least partially the information that are in those files. So those are among the reasons one needs to identify file formats. So for this particular task, our primary objective was not to create a new technology from scratch, but first of all, examine the existing technologies for identifying file formats and find what might be the most promising or robust technology for file format or file type identification and advance this technology to meet the requirements of the National Archives. Just a few definitions. A file format usually is in the form of specifications that are either published or not, and essentially this is a set of rules for encoding or decoding the data that's used by a computer program, or encoding the computer instructions of executable files, like a software application like Word. And by a file type, we'll mean a class of files that have the same file format. And a file format signature is some type of invariant data that's in a file format that can be used to identify that file type or the format of a file. Okay, in addition to these internal file signatures, we need, or the archives needs, some sort of external file format identifier, which is an identifier that's linked to the file, so you don't have to always examine the internals of the file to determine its format. You've previously determined this is the format, and you can just refer to that metadata. Well, these are among the types of external file format identifiers, really the most common. First of all, there are what originated really with Microsoft file name extensions, which we're all acquainted with from DOS, that were 3-character file extensions to 8-character file names. And now with more recent versions of Windows, you can have longer file name extensions. And essentially the operating system is, or file system for Microsoft, is checking the file extension to determine the file type. But that's external. It's a file name linked to, that's really in the operating system, okay, or the file system that's linked to the actual file. There's also metadata, other metadata stored in the operating system that can be linked to the file. For instance, in the Apple Macintosh operating OS hierarchical file system, this was for early Macs, there was what was known as the creator code and the file type code. And I won't go into the details of those, but they were codes that were stored in the operating system and linked to the file to identify the file type. The current Mac OS X has version 10.4, I think, first introduced what's called the uniform type identifier. And again, I won't go into the details of that at this time, but it's another external identifier. Multipurpose internet mail extensions were MIME types were initially developed to configure email clients so that when email was received that had attachments or files that were associated with them, and multiple files, that one could determine what kind of file they were for display purposes. And those were extended to configure web browsers for a similar purpose, so that you could identify the different types of files that might be on a web page, for instance. And then more recently, the National Archives, TNA, of the United Kingdom has developed a registry for file formats. The registry is known as Pronom, and in doing so, they have created the notion of a persistent universal identifier, or a PUID, that is associated with file formats. And the idea, of course, is that this would be sort of an international registry used by many archives, and would be a standard for an external identifier to a file format. Well, one of the file type identifying technologies that has really been around the longest is, we feel is one of the most promising, is that of the Unix and now Linux file command and its associated magic file. Magic number is the term that's used in the Unix community for the concept of an internal file format signature. And the basic idea is that it's a number that was created by the developer of the file format that's usually stored in the header of the file and that can be uniquely used to distinguish it from other files. And so in the Unix community, one could write their applications knowing that they could check for this magic number in the file header and know that they had the appropriate file type. And some developers in the Microsoft development community have adopted the notion of using magic numbers as well. Others have developers, there's no standard for file signatures or magic numbers, okay? It's sort of at the option of the developer. What the file command does is it applies tests or patterns that are stored in a magic file to an individual file to determine if it fits one of these patterns. And if so, it outputs the name of that file type. It also has the language used for defining these patterns also has the capability to check for additional kinds of metadata that may appear. So for images, it might be able to, if the metadata is there, to determine like the dimensions of the image or the resolution, or colors, monochrome, audio, for audio files, sampling rate. One might have captions that are associated with things like image files. And so the file command plus magic file also has that capability for extracting metadata. And this technology has been around for at least 25 years. In some version, it's been around even longer, like 35 years, but its current instantiation, and it's up to like version 5, I think. It's been around for about 25 years. So it's a fairly mature technology. Here is, okay, the magic tests are currently stored in text files in 112 directories, and for management purposes. And they're named with things like the application type, like word processing. And I've pulled the first part of one of those text files out, which indicates that this is the portion of the magic file that's for word processors. And one sees a test here for a file format used on the Smith Corona persistent word processor. And then in the left column here are what are known as offsets into the file. So this first line with a 2 there is indicating at the third byte. So we're starting counting bytes at 0, 0, 1, 2. There's a string, and this notation off at the right is indicating check bytes for an octal 40 in the first byte, sequence of octal 40s, and then a character ML 4D, a sequence of 4 characters, and then another octal 40, and then it looks like an apostrophe 92, okay? And output that this is a Smith Corona PWP file. But then at offset 24, check a byte to see if there's a decimal 2 in it, And if there is, output a blank and indicate that this document is single-spaced. So it's metadata. If it isn't a 2, it might be a 3, in which case it's 1.5 spaced. If it's 4, it's double-spaced. Then check byte 25, and if there is a hex 42, indicate it's a letter. In that same byte, if it wasn't a hex 42, it might be a hex 54. If it is, output the fact that it's a legal size page. And check byte 26, and if it's a 46, output A4, and I have no idea what that means. Okay, then there's there's a test for a variety of WordPerfect files. Now these are not all user-created files. Some of them are system files. But one reason for showing you this, like for instance, all of the WordPerfect files here start with, oh gosh, let me see, /377. Well, they have a WPC, a string that has a WPC in the header, and there may be something like an octal 377. That looks to me like, yeah, that's FF at the beginning, I think, of the file. And if there is, you output WP loadable text. Then check for optimized for Intel, optimized for non-Intel. Now, if those tests didn't work, look at byte 1. And if there's a string WPC, output that it's Corel WP or WordPerfect. But that's not all you do. Then check, and for instance, if in byte 8 there's a short integer 266, that indicates it's a WordPerfect document. But if it's not a WordPerfect document, it might be some of these other file types. Now, one of the reasons I wanted to show you this was there's not a one-to-one correspondence between the tests and the file types. Okay, so the tests are constructed for many file types. And that's one of the disadvantages and limitations of the current management of the magic file, is it's very complex to find where the test is in the first place. If you've got to add magic tests or modify magic tests. And so that's just a quick illustration of some of the complexities. So here are limitations. As I just indicated, it's difficult to update the tests for magic numbers. There are tests that may give conflicting results, and one needs to properly sequence them. For instance, docx that Microsoft introduced for Office 2007 contains the information for a Microsoft Word document. However, it's packaged in a zip file. So if you need to know about zip archive files that are not docx files, you need to first sequence the test so you're checking for a docx file before you check for a zip file. Because if you don't, you will conclude that it's a zip file and not know that it's a docx file. Okay? And as I indicated, the tests for magic numbers are not one-to-one with file types, and that is a difficulty in managing the tests. There are tests that output metadata as well as the file type, and while the metadata is important, if you're only interested in the file type, you need to have some tests that do that, and you can create another sequence of tests that are specifically for metadata, if that's your interest. Okay, the file command to check for text files and what kind of character set, like UTF-8 or ASCII or UTF-16, And language. You know, is this English or Serbian or Arabic? This can depend on character set as well. It does these tests after applying all of the magic tests. And one of the issues here is that we have a lot of file types, like let's say Fortran programs, or script files for Unix, or batch files for Windows or DOS, that are text files. And one may want to identify those as file types, and strictly speaking, they don't have a magic number, okay? But you want to indicate they're a text file, and based on the character set, or sort of the kind of statements that appear in it, like Fortran statements or C program statements, that it's a C program text file, or a Fortran text file, or a COBOL text file. And those tests come after the test for magic. They are hard-coded in C. And the descriptions that are given are not something usually as simple as ASCII text file. They are ASCII text file with carriage return line feed, or C program, and one wants to be able to manage, for archival purposes, what kind of descriptions are being output and how much information. In other words, the current magic and file command are outputting a lot of metadata that you may not need in order to identify the file type. And in another case, you may want to know all of that additional information. So it's a current limitation that you have to dig into the program code in order to address those file types. Okay, there are only a few tests for Microsoft Windows file types. This is because this technology grew up in a Unix, Linux environment. And many of the files that the National Archives are going to receive will also be produced on Microsoft Office application software. So we need to have coverage for those file types. If you run your own test of the file command and its magic file, you'll find that it gives erroneous results. And that's because the tests of the magic number tests in the magic file have not been systematically, rigorously tested. So those are just some of the limitations. So our approach is to overcome those limitations, okay? And to do so, we've created a file format. We are creating a file format library, which I will demonstrate in just a moment, that contains information about the file formats, including links to specifications for the files or documentation of reverse engineering of the file formats. That includes sample file formats, and we're trying to come up with samples that can be distributed and shared by the research community and by archives. And so those will be files that are in the public domain or that have been put into the public domain. We are creating our own magic file where, if you like, where the tests are for individual file formats and not for the metadata. We're outputting a file format ID rather than a name or description, such as done in the file command. And one of the reasons for doing that is there's many aliases there's no standard for file format names. Now with the pronom registry, we have the opportunity for a standard for file format names, and we have the opportunity for a unique identifier. And it's not, so let me say, It is not our goal to become the standard. Okay, this is just research that can support something like the pronom registry. We're rewriting the file command code for identifying the characteristics of text files and different document types. We have defined approximately 850 file format signatures. The current file command, or the magic file for it, if you carefully look at it, it has more than 2,000 tests, not 850. But many of the tests that we've created do not exist in the magic file for the Linux command. So we didn't go there to get our information. We did things like look at pronom and the files that are in the registry. And we looked at the files that we were encountering in our research for NARA as to which ones would be important. We've collected examples of approximately 650 of the file format types. And we're collaborating with NARA's InCast laboratory at Rocket Center, West Virginia, with Mark Conrad and student interns there who are helping collect samples of federal records that are available on the internet. So they're already in the public domain that we can use as samples. And they're focused on helping us. They're also helping us collect file format signatures, and that kind of information is going into the library to support our research and development. Well, the file signature database is a part of the file format library. We've verified that we've created a file format identifier that's based on the file command, but uses our magic file. And we've created an interface to it that I'll show you. Okay, I've entered this by saying I wanted to look at the file formats, browse the file formats that are in the library. And I've gone down to the last page of all of them that are in, I thought, oh yeah, it's there. And you can see the second column there has got an internal file format identifier, and we're up in the range of 850 file formats. And in the second column, you see the primary file format name that we're using, an indication in some cases of a version of that file format. The MIME type. Okay, one of the big issues is creating a unique identifier that's external to the file. The PUIDs, as you can see over in the last column, many of the file formats that we have in our library do not yet have a PUID. So there's not a unique identifier for it yet. So one of the things we considered is, could MIME be a possible unique identifier? And we think it can. By using some of the features of the MIME definition, we're able, MIME types are registered. And so there's, but there is not a MIME type that has been registered for all file formats. But there's a feature of defining them that says if it's not in the registry, you can prefix an X and a hyphen to some name that you create and extend the names that are available. So we have endeavored to create a unique MIME type for each of our file formats that are in the library. There's also the concept of parameters that can be defined after the MIME type and subtype. So for that first line there, we have application / and there is not a MIME type for word star, a subtype, so we have X word star. And then we've created a parameter called version and indicate it's version 5.5, I think, if I'm reading it correctly. And Similarly, there's version 6 and 7. And that is unique as compared to all of the other MIMEs that we've created. Now let's look at some of the information that we actually have. Let's go back here. Okay, let's look at 3D Studio. Okay, for each of the file formats, we have this kind of information. Okay, its internal ID, its name, a version. Now, we haven't entered all of the information for these file formats, and this is what the student interns are helping us with at Rocket Center. Who was the developer? What is the application or applications that create this file format? Which operating system does this application work in? What's the date, the first date that this file format was used in an application? What are the possible file extensions? Our MIME, the PUID, pronoun unique identifier, if there is one. Okay, now here's something that's experimental. We want to name the class of objects, see if we can categorize the class of objects that are created by these applications. And so this is a tentative taxonomy or ontology, if you like, of the kind of objects that are created. And we've said here, well, there are graphics, and this particular class we can characterize as being 3D digital objects. By application class, we mean the kind of application that created it. For instance, for text files, we might have word processing kind of applications, or desktop publishing, which are similar to word processing but have page markup, page description languages, anyway, things like that. Family, I haven't entered here, but by family, that's it, we mean file format family. So for instance, you might have a Microsoft Word file format family where 3 or 4 or 5 versions essentially were the same format, but there were minor changes to the format. This is important to us because we're interested in another research problem of characterizing the structure of those file formats outside of file format specifications. And it's just a different approach to support preservation, conversion, and viewers. Okay, I'm going to move forward here because I'm toward the end of my time. Then we've got the magic and a description above it of what features the file format we've used to define the test of the internal signature. So it says this consists of a primary chunk ID, chunk length, version subchunk ID, chunk length, version 3D editor chunk ID. And I'm not going to go into the details of that right now. We've got here a citation to the information we use to define that test. And we've got a link to the source. And that path file name, the idea there is we're thinking about the possibility of keeping one copy of this specification in sort of a deep archive. It's not something we would distribute, but just for the National Archives for the indefinite future to have a copy in case it disappears from the internet and they need to know 25 years from now, okay, what the format specification was. We haven't entered a viewer or player or for this file, a viewer in this case. But the idea is if there are commercial or free viewers out there to indicate a link to where they are and their name. And then finally, examples. And this is a description of the item, of the 3D. It's not a record, okay, but it's a description of the item. And the rights that we've identified and the source. So if you clicked, I'm not going to do it here because I have other things to show. Clicked on this link, you'd see where we got that file. And again, we're saving copies of these, and what we're aiming toward is to get files that are in the public domain that can be shared. Okay, let me stop that and finish with a quick demonstration of the file format identifier. Okay, so this is a user interface to the file command. The file, I need a slide that shows you the output of the file command. And I'll say something about it in a minute. Okay, let's open some files. Okay, we've put our 650 examples into some subfolders. It's not necessary to have separated them by folders, but it helps in just demonstrating, for instance, applying the file format to word processing formats or 3D graphics. Let's just do it on the 3D graphics. So these are the paths to different types of files that have 3D graphic file formats. And if we indicate we want to identify those files, we have not, well, here they are. They're identified. Now, what happens with the file command is it outputs a path and a file type. No, and a name, and some metadata. Then we want to have some control over what this identifier and the database up there gives us is the ability to structure what the output should look like and tailor it to what you need. So what we've added here is MIME type. You might just want to see a MIME type if it's unique, or one could be outputting just the PUID. Now here we've just shown the various types of external identifiers that could be used for it. We've verified that they're all correct. There's 3D Studio version 3.4s. And below that, there's QuickDraw 3D metafiles, AC 3D 3D models, Blender 3D. Now, a quick comment here. These may be files that here in your job at the National Archives you're not currently encountering. This particular set of 3D file formats we collected in collaboration with the group at Rocket Center and Peter Bexey at NCSA, University of Illinois, because Peter is looking at collecting tools for conversion of file formats and looking at issues and information loss in those conversions. And he was particularly interested initially in 3D file formats and CAD file formats. And the National Archives does encounter in some of its agencies, like DOD and in the Navy or Corps of Engineers, CAD drawings, okay, and 3D object representations. And so, and you can see there are a few PUIDs, like for the 3D Studio. Here's some others. Rhino CAD models, SketchUp, Google, and VRML files. So anyway, there's a quick demonstration, and I'm ready for questions.
Thank you, Bill. Thank you.